still forecast were happening. No, we were IMD and Government of India were doing the forecast. Anybody remember 10 years before how was the forecast? 2012, 2010. Yeah, actually, if I have not heard many seminars, it is not happening due to online things. But a lot of seminars happen, then people tell, especially the monsoon people, if anybody from Surya Sir's group, even Surya Sir is giving any talk, any chance you get, he will tell starting 100 years before how it used to happen, and then what is happening 10 years before, everything, whole history. Even whatever, I mean, from they are telling, I'm not from that, I mean, modeling, I'm a small scale, but large scale people, the forecasting people are saying 10, 15 years before, even there was no surety that whatever we are forecasting, it will happen. But after coming to Aditya and then Pratyush, and this cyclone forecasting and all things is really very accurate because of the computational things. But this is all large scale is going good and good. But now the problem is local projection, extreme event. How to do that? Still, our highest resolution in IITM is happening. What this GFS, the short range forecast, 12 kilometer, no, highest. But normally we are doing 35, 33 kilometer. That, yeah, 33 kilometer. That is the normal from the CFS. So even 12 kilometer is very difficult. Too much computational things. Yes. So the idea here is that we run on 100 kilometer. The global model is normally running on 100 kilometer or even higher. Higher means lower resolution. So then people try to do some kind of data downscaling to get the local area. Okay, so how they used to do? Yeah, one more thing. I before that I wanted to go for the what are the data, but I think if you are only the student here, then I don't have to repeat it. I have already told. But if somebody is there in the online, I have to check. No. So there is nobody from outside. Okay. So I'm not repeating this. What is the data? Because you already know through this. You remember or not? What kind of data we are handling? Just few examples I gave in my previous talk. Interaction talk. Student interaction. No, not forward. Yeah, what kind of data generally we are handling? Just few data in the atmospheric only. Yes, observation, but there are some example. Maybe I can go through that. So, like very important data is the ground observation from IMD. So we have our ground observation, the weather stations. We have many stations. IMD is across the country and thousands of thousands. I mean, many thousand, 8,000 or 6,000 something. Till now, we have the data to around more than 6,000 stations, which is developed, created in 2014 by Pi et al. People. So that data is really, and they are collecting the data every day. So it's a daily data. And last starting, I think 50, 60 years, even somebody saying even 100 years data we have from the British time. So they have very nice inventory. They keep the data very nicely, and we continue that things after that. So that thing is very good treasure from the IMD. So that data is very important, and most of the people using that data as a ground truth for their model validation and all. So many things. So, but that data is on the ground only. Okay. So what are the suppose you are using the data for your AI algorithm. So this one I discussed last time. So if you are using the data and especially for the deep learning things where you have a spatio-temporal and where you have to use the convolution. So when it comes to convolution, what is the main property in the convolution? You recently, I mean, studied this convolution for the image, how the convolution happens in the image processing, or something was told in the class, no? So what is the convolution in general? But you learn, no, in the class, there is a CNN. CNN was taught. Yes. So CNN means convolutional neural network. So any algorithm where we are using the convolutional convolution, what is the convolution? I think it must be told in the class by the examples how the image is scanning through. Was it told? No, I think you will only told that it was taught in the class. So any idea what is the convolution? Okay, what is the how we represent the data? Suppose this is image, RGB image. Simple. You can consider a simple RGB image. Forget about the meteorology. So how we represent the data in computer? Either pixels or something. But when we represent, there is a one thing is the pixels for the image. Okay, but the pixels has some kind of representation. It might be binary. It might be some other number as well. But if you talk about the data structure, come to from I mean now from image to mathematics, like data structure. So then, what we call in mathematical term for this data? Matrix. Yes. Now we are on the track. Okay. So any image. Now I'm not saying image. You got the idea, no? Why I'm saying any data, our meteorological data, we are representing as a matrix. So when you do the neural network, you are doing some kind of operation. But if it is only time series, we just do operation on the particular data. When it is a spatio-temporal, means when we have the location and we have the time, both the things, that is called the spatio-temporal. Then we are applying the convolution on that. So convolution is a small matrix which we generally scan through this big matrix, the data matrix. So generally it is 3 by 3. What is the example told in the class? 2 by 2, 3 by 3 matrix for the image scanning. 3 by 3 is a square matrix. So slowly I'm coming from simple image to the data to the mathematical language. So now we are talking about the square matrix. So when you have a convolution as a square matrix, we generally want to have the whole data we want to have in a square matrix as well, not the rectangular matrix. Okay, this is what in principle we do for the convolutional neural network. So when we take any this kind of data, first thing is we don't have a square map of the India because our IMD observation only on the ground. So it's a ground automatic weather station which is not in the ocean. So the data available only on the ground. But when we are applying any spatio-temporal algorithm of CNN kind of things, convolutional neural network, we have to have a square matrix. So we take the data in this area for all Indian subcontinent, including even the upper part, this lower part of China, southern China, everything. We just want to have a square. So that data we take. Then what is the problem in that data? Suppose there is very specific algorithms where we have to deal with the specific value. They are not only 0 or 1. It's not like image processing. When we come to the precipitation, we cannot say 0 or 1. We have a millimeter per day. If it is a 0 millimeter per day, that means we are saying there is no rain that day. So when we say the data is available on the land, that means for the ocean, we don't have the data how to deal with this when we are applying any AI algorithm. So if you take the real data, original data from IMD, we generally have a very big negative value, -999. Okay. But within your experience last 3 months, if there is a data which is basically suppose I think this is more than less than 50%, which is not the land. If you see around 50% or 60% is the land in this data. So which is suppose 40% data which is having no meaning at all, minus negative. Can you do the training of this data? So what is the training means? You are taking the data and then calculating the weightage. You know that function, approximation function, initially it was told in the class, in the machine learning class. So when your approximation, you are just calculating the weightage based on this input data value. The value is minus 999, but the real value, what precipitation happens from 1 millimeter, 0 millimeter per day to maybe 100 or something. That is the even extreme, but not minus 99. There is no negative precipitation at all. Either zero, I mean, it's like a greater than or equal to zero if you put the inequality. So when it is a negative value, how to deal with? So for that, we have some strategy. I'm not going in detail. So in this case, like we are saying the non values, we put for nan values, but this nan values sometimes is not useful when you are going for some kind of forecasting problem. But in the downscaling, it is okay, we can do, but it is not always good. So we have to deal each data differently. So whatever the thing you do during your PhD, you have to deal in your own way. So the scores which you have been told in climate data science, that is the meaning. Whether it's your radar data or your this extended range data or your this one biomass data or your using, everybody has its own way to deal it, to do the proper training. So this is what I wanted to tell how the data. So this is like precipitation data. We have the problem of this is not called the missing data. This is just a data which we even don't have. Missing data is still if we convert everything in our format, some transformation, mathematical transform, something we can do. But still we will have some problem like this. Some weather station is not working at that particular time. We have a missing value. So handling the missing value is another area, or you can say another issue point in this. Okay. Who can tell what is this data? NEE, net ecosystem, ecosystem extent. Speak. It is your area. You know this, no? Okay. So generally, what data we are getting in whatever the source, it is a global data. But when you are doing PhD, you will be first focusing on your area, because we want just in the Himalayan area what is happening, how it is changing in the decades and all, or what is the seasonal thing change. So we have to worry about only our area, including Himalaya. Like previously we took up to this China and also. In this case also, we are focusing in the Indian subcontinent, including the Himalaya area, because that is the region where which is affecting our climate, our country climate, or South Asia climate. So here what we have to do, data is available in entire globe, but you can cut it. But this is very simple. Whatever the location we want, we have to do only that much data. But this is, I am saying that this kind of problem comes to handle the data. So compared to the whole, this is the whole globe data, we can take only that much. Okay. You should recall I have told all those things in previous talk. So then we can do our data pre-processing, apply the algorithms and something, and some forecasting we can do. And this is, I'm not saying what how many days forecast something. I think for the any one day forecasting no meaning. We need here seasonal 3 months or 6 months. But this is just one example I'm saying. Simple like a lightning data. I mean, this is fire inventory data. Do you remember I talked about this? Everything in forward, no? Just 1 month, 2 months, how many? 3, 4 months before your semester start. So lightning data, I discussed this. I mean, fire inventory data. This is coming basically from the remote sensing. And the remote sensing is, again, it is the whole globe data, and a lot of variables are there. And the data goes in terabytes. So again, we have to focus some particular area, or we have to do some kind of the pre-processing, or we can cut it just one particular variable. So in this case, we can take PM 2.5, and then we can leave all other. So anyway, so we have to see the data, what to do, whether spatial location, or like in this case, we have the data for the whole India. The sensors, you know how many sensors we have, IITM, for the lightning detection? General knowledge question. 83, I think we have now. We are planning to buy more, maybe 10 or 20 more. It's very expensive item. it takes. But we have covered almost all the India, but still we want to increase. So this whole India is data is available, but if it is bulky, generally it is not bulky. Like fire inventory, this data is in 5 terabytes, but this will be in megabytes on gigabyte. That's all. So how to handle the data? And in this case, you see the properties. The one thing is the data format, another is data size, another thing is the range. So like in precipitation data, we have -999 whatever. In this case, sometimes the intensity, light intensity going 3 lakh ampere or -2 lakh ampere. It is not happening all the time. It happens somewhere in the cloud to cloud, but not coming to the cloud to earth. I think somebody gave the presentation. No, you gave. So what is important for us is coming from cloud to earth. That is important. That is creating problem, casualty in normal life. But this maybe this 2 lakh or 3 lakh, whatever is happening, might be happening within the cloud. We don't worry about it. Let it be. So what is important for us? We can take a range from, suppose we say 1000 ampere or something, some range up to 60,000, which is generally happening and which is really harmful. Sometimes it is very high ampere, very high intensity it is coming, but it is going in the water and it started exploding the water in the river and all. Maybe sometimes you see the video is available on YouTube. Very high lightning intensity. Okay, so just one of the few examples I gave. Now I am coming back again. The question is the data downscaling. So I am saying this machine learning downscaling. So again, question comes, why we are doing? Suppose this is observation data, and I'm saying this is suppose I think 25 kilometer. The resolution is saying it's 0.25 degree data, and we have this data. So this is observation data. Suppose this is observation, or we have a model data. We got the output, or we have this data, but still we don't have the information within 25 kilometer. 25 kilometer means 1 point in a city. Within Pune, you will get only 1 point. How will you know that what is happening in the different part of the Pune? Talk about Pune, Mumbai, all the big city, Delhi. The radius is going 50, 60 kilometer. So within the whole NCR, you are getting only into the New Delhi or in Pasan or somewhere. So this is the need that we want to go for a local projection. That's why we do the downscaling. Is it? You have to tell now. Yes. Otherwise, you will sleep. This is lunch time. It's a bad time for class. Okay. Anyway, I also feel sleepy after the lunch. So today I have to take early lunch even. I go 1:30, 1:40 for the lunch. So observation data or output data, this is all really less helpful to understand the local projection. It is whether weather, climate, agriculture things, anything. Agriculture is always affected. Suppose you don't have the information of the temperature or the even precipitation at the local level, you are not telling any useful information to the farmers, which is the main thing. What we are doing for weather forecasting, to know the monsoon, so that our farmers should get the information properly and the crops should be better. That is the whole business or whole idea about this Indian monsoon. Understanding is difficult, no? So we have to do the local projection. Okay, so just look at this. I am saying that if we have even higher resolution from 25 kilometer to 12 kilometer, 12.5. So what is the difference here? Look at this area. We have only one spot. But here we have got so many local these patches. Yeah, many places. Even the intensity is changed. See, look at this area, northeast. Northeast is difficult in the model because of, I don't know, maybe there is a chicken neck or all. So the boundary condition has a problem. Some problem in the model. I am not going detail, but generally capturing these values here in the border areas is difficult. So this is the actual data we have. But if we go for the higher resolution, we have so many different points here. At least we are better. We can tell all those points which we are saying, no, there is no rainfall here. It is saying 0, but it is saying some value here. At least we are coming up to the between 20 and 40. So this is the advantage, that we can give some local information. And all this study research is going here to improve the weather forecasting. At least, not at least, we have to improve to go for the local projection as well. We have improved already for the general forecast. So the downscaling is happening even before. So this was the IMD data, observation data, whatever, IMD observation data. This is CFS or output. CFS is, we are running for globally. Mostly we run for the globally. I just took some patch. I'm generally focusing only India area, India subcontinent. So this is the output. The resolution. We have the output. We can say, okay, we got it. This and this is the intensity. This is what in the Western Ghat happening. This is what it is happening in Nepal and Himalaya area. But if we have the better resolution, 4 times better, then look at the situation. Now we know where is the higher intensity. Where is the higher value? So these patches, red patch was not there. The precipitation is higher. It's going up more than 48 that area, which was not possible, not visible here. So even in the Western Ghats, we have different patch here. Pattern is different. So this is what we are doing in the downscaling. But running the CFS at 100 km is easier in terms of the whatever the facility we have available here, because we have to run and we have to finish within the time and do the forecast. Running 25 km is difficult. Global. It may take more time. And if we are giving a forecast for the next 2 weeks or maybe go for short runs, generally short run we have to go up to the 3 to 4 days, 5 days. And if it is taking 1 day to run, then what is the use? So that's why we run whatever is reasonably, we can run faster. And then we can do some data post processing. Actually, downscaling generally we can say post processing part. Okay. So how we do? So somebody told that some okay. So we used to do this, we still do. We do the regional model, we do the downscaling. But still, running those regional models is not easy. They will also require thousands of the cores on your HPC. And maybe a couple of hours or 5 hours or something to run. It is not also easy. And when you go for regional, suppose you want to know the higher resolution information in the whole India, but when you are running a regional model, you will be running in a particular region. So how many such a models you have to run? If you are running parallels, then how much bigger HPC is required immediately? If parallelly everything you want in the same time. So still it is a computationally expensive. So few, about a decade or before that, we used to do the statistical downscaling. So the statistical downscaling means we can do the interpolation. Whatever the better and better interpolation, linear, bilinear, or we can go higher order also, polynomial or whatever. We used to do that. But still we have the numerical error in that. Slowly we are moving, starting from 2014-15, we are starting doing machine learning kind of things, AI ML application for the downscaling. So the first thing came, so this is what we are going to discuss. So the first thing it came super resolution CNN. So directly I'm talking about the deep learning here, CNN. So super resolution CNN. So in this case, we take just one image, single image. We try to make a higher resolution. We have to see the time. whatever happens in today, I will do, then I will continue tomorrow. So 2:30, still half an hour we have. So you see, this is a diagram I made, which is given by the, I will tell who, this is Dong et al. The next slide will tell, but this is the concept I'm saying. A single low resolution image is scaled up to the desired size using the bicubic interpolation. And then that one we take as a input here, and then this interpolated image is being putting into this algorithm, different layers, and finally we are generating a high resolution image. But it's not like the whole image is going. The idea in this algorithm, this is called the SRCNN. Take one particular patch, pass through this algorithm, get a higher resolution patch, put it in that figure, I mean the high resolution image, then take the another patch and keep doing this. It's not like iteratively, there is a way that you can go everything, but you take one patch, make the higher resolution, take another patch, and then slowly we are making the higher resolution image. This image means higher resolution data. So this algorithm works as a like a image processing part. If you just talk about the basic image processing, they have used this idea long back, or they have been using. But then slowly we, in 2014, Dong et al. Said that the same image processing idea can be used for our precipitation data or any meteorological data, temperature or humidity or whatever. Okay, so what they are saying that this is the data, observation data or model output data, but I am saying this is image. Can we say? In general, image means what? There is a XY coordinate, RGB value. We have the latitude, longitude, we have the precipitation per millimeter per day. So this is our RGB value, and this is X and Y. It is also image. We can apply CNN here. So whatever they did for the image things, we can also do the same thing. We can take one particular patch, pass through this algorithm, and get a higher resolution patch and put it into the higher resolution image. So this happens all together. I mean, when we do, so taking the patch and doing this is what the idea given by the Dong et al. 2014, and then in Wendell et al. 2018, they apply this thing for the precipitation value. Whatever we are showing here, they applied not for Indian data, they applied for the US precipitation. And they said, yes, this algorithm is working for the precipitation data. And that is what we tried here. Just 2-3 years before, when the last year paper came, 2 years before. So we also tried. We all people here, we some master student, one me and Rajiv all. So we thought this idea we can apply on our Indian precipitation data, whatever they have applied. We did that. Now think about this again, data preprocessing. So input we took the 1 degree, that is the 100 kilometer, that the size is 33 by 35. Then we generally do a linear interpolation, which is the input for that algorithm. Simple linear interpolation you do. All the data cleaning, which I told that negative value we have to put it the NAN. NAN is working in this downscaling algorithm. And then what is this transform, the last image? So low resolution is 33 by 35 image. I think all this number sometimes I mismatch. So this is the 4 times higher resolution. So it should be 4 times of this. Maybe some, but even then we are transforming it. Why? This guy, this image, and this image. Why we came from here to here? Today only I told. No, that I have done. So negative value I have put the NAN value. NAN value is okay for this algorithm. Okay, for training purpose, it will not take any value here. But everything was fine. What is the difference from NAN fill I am doing because we are doing some kind of transformation. Now for doing that transformation, I am using the NAN value. But why I am doing the transformation? A square matrix. It is a convolution. We have to apply a convolution 3 by 3 or 4 by 4. So then we need a square matrix, and this guy was 129 by 135. We made it 140 by 140 by filling the name values all the way. So it becomes a 140 by 140. Just an example, whenever you have applied algorithm in your data, even your term evaluation, you have to see all those things. These are the, you will get the better marks if you tell the algorithm properly. Okay. So we are making this the first arrow, then converting all negative value Indian boundary value to the NaN. Then wherever it is required, we are putting just dumping the NaN, and then we are making 140 by 40 as a square matrix. So now the data is ready. We have done pre-processing. This is just what we are showing in the 3 arrows. It is not a simple things. You have to write 2-3 routines for this to do all this. Whatever one arrow is one routine, you can say. Okay. So do you understand this? This slide? Speak out something. Yes, Sangeet.
Actually, first it is an activation function.
Why we need?
Because we want to trigger that node inside the
okay.
Network. So at that time we are using that function. So PRAU, it is one of the function there. Then
parametric value.
Yes.
Remember the names, because lot of new activation functions came in the literature and which are better than ReLU and all.
Then there is a kernel initializer. That is it is actually that kernel helps to overfitting, that helps to avoid that. Then we are using the optimizers there.
Optimizer is for what? Any idea why we use the optimizer? For what purpose? That is also told in the beginning. Machine learning algorithm. Optimizing of the convergence of the algorithm. We are going the gradient way, no? There are many other way, and there are many this one optimizers came in the, this is all mathematical optimization optimization theory, which is a very old theory in mathematics. So what is the full form? I forgot. This is very good. So this is the best optimizer suitable for many of these deep learning algorithms. And then why we need a loss function?
Loss function we need
maybe now next person, Nikhil.
To calculate how much the value we are getting from machine learning is actually deviating from real value.
Deviating from real value. So basically, what we are doing in the training purpose, we are calculating the weightage. Okay. So weightage, how we will calculate? Every epoch, even within the epoch, there are many epochs also, no? Backward forward. So every time we are in one epoch, we are actually updating the weightage. How we are calculating? There should be some base. We have our predicted value, approximated value, and we have a ground truth. We take the difference or some kind of metric, not say difference, any metric. Based on that, we will calculate, no? So this is updated weightage, then again update, then again update. So those Wi, Xi, the formula, na, Fx, Fy is equal to Wi, Xi. So W weightage we are calculating, we need some kind of the loss function. So here we use the mean square function. We can use the RMSE also. There are other methods. So till now, many people, this Dong et al. And all this SRCNN kind of things, even the convolution for downscaling, they all are based on the mean square function, RMSE or MSE. Okay, but not all the functions, not all the methods. Okay, so then best size epochs, Priya?
Sir, one epoch is when one forward and backward propagation step.
Okay, so within the epoch, we just get weightage updated only once or twice?
Once.
Voting once or twice.
So So in backward bits are
When we go backward, then we are updating. No, that's calculating based on the loss function and the learning rate. This you should know from your undergraduate background. When you do any iterative methods, we need a threshold value. Here we call them learning. So till how long we keep on going iterating. So there should be some criteria that when the error comes up to that threshold, we will stop our iteration. So that is the learning rate or the threshold value. Did you heard about iterative methods for any kind of iterative methods, even for interpolation or polynomial things? There is iterative methods. Whenever you do iterative method, you put a loop, but then you put while error is less than th, the threshold value, keep doing this. So that threshold value is the basically we call it the learning rate or this. But in our case, it is not simple iterative numerical method. In our case, we have the adapting method. We can even change the learning rate during the training time. We change also depending on how the progress is happening. And also the data is important, how much data you are giving for training purpose. Okay, so what we are talking about, we have to remind what I am talking about now. The deep learning downscaling, the method is super resolution CNN. Okay, till now I talked about only one single input is the precipitation, and I'm talking about all technical details of the algorithms. These are the technical details. What is the activation function, loss function, this and that. So I don't have to tell what is the training and testing. That is the, I think, very basic things when you learn. So whole data, whatever 40 years data we had, we divided data into training part and testing part. And so now you can understand, because I have shown so many figures, what is happening in this algorithm. Maybe just one part, the training part or testing part, something. So we have this low resolution. We are making the interpolation, then giving it to our model, training or testing model, and then finally we get the higher resolution image. So what is in the model, what is the architecture of the model, some part I told, but this is the way it is going on. So the main thing here is that it is a single image super resolution algorithm. We take single image, we take the patch by patch, and if you go to the original Vandal et al. Or Dong et al. Paper, they have Dong et al. Have basically only the image processing. They have a butterfly figure and all. They will say that take this feather and there's one patch and go there. The same thing we do here for the precipitation data. Now, SRCNN is okay, no? Single image, super resolution. Now, what they said, even those same people who developed this algorithm, they are saying that we take the image and we are going 4x resolution. Direct. We apply our image, we are giving the training in such a way that we can go to the 4x resolution. But then they discover, when you do the things, you have the idea in your mind. Now we can extend our research. Whatever you do, master or PhD, you will say the future scope is this. Once you do the work, you will feel that we can do this way. So they are saying that going directly from here to 4x, suppose this is 4x. If we do this SRCNN just for the 2x, 100 kilometer to 50 kilometer, again apply the SRCNN here, go 25 4x, again apply, go 8x. Suppose we restrict only 4x. So whatever we did before, directly for 4x, we will divide into the 2-step, like ensembling kind of thing. So we are saying the stacking. So we are doing the SRCNN, same data, same algorithm, but instead of one time, we are doing 2 times. So when the output is coming from the one step, we are giving this as an input to the next step. And this was the successful experiment. They said now we are getting the better result because it has improved something in the first step. It has extracted the patches, made the high resolution patches. Then again, I am giving the same algorithm. Again, it is starting improving that patches and making the high resolution image. So this process, iteratively, it is going. It is better than going direct in one step. So this is called the stacked This is all well done in the image processing, and the same thing worked for our, at least I will say, precipitation data. I have to say maybe other data. Precipitation data people have done, we have done here also. Now just think about from image, normal image to meteorological data. What else we can do here? What else is responsible for precipitation? Very direct I am telling. So in the images, this is just click image. We have the pixels, intensity of the pixel, density of the pixels. Density means how much the RGB value we are taking, or frame rate, or whatever the optics you can talk about. But still, this is all about the pixel quality. That's all. We have nothing, no other information. X, Y coordinate and pixel quality. Same thing we have in this our precipitation image. But we are beyond that. It is a natural phenomenon. So what is beyond that? In your how many variables are responsible for the net ecosystem exchange? It's not only we are saying net ecosystem exchange, just one NE data. What is inside? How this data is prepared? Combination of many gases? No. This is a net ecosystem we are saying, but inside this dependent on many things. So when the monsoon is coming, the monsoon we said is coming early. Then they said no, it's stop. Then again, today it is onset. It happened 29th. This so uncertainty. It's not like a camera picture that we have said this is the pixel quantity. It is really definite. It is not. You are seeing very nice example this year. Today 30th. No, the monsoon onset came yesterday. IMD already said it will come 29th, around 29th. But initially they said it may come 27, even Maharashtra, but then it got stopped. Why it got stopped? They are natural phenomena. We don't have control on it. So that means even this monsoon is precipitation. Precipitation is depending on many other natural things. And we are doing the learning process. This is the artificial intelligence. Artificial intelligence depends on our experience, our data, and what data is experienced, that I have to tell to our algorithm. Okay, so what we have to tell? We will tell that all of a sudden in the Kerala, the monsoon, the rain came on all Kerala, not only Kerala, in all the South India, because of there is a large vortex form. All of a sudden, this was not known. The vortex form, so there was only for 1 week, so heavy rain and all this from Karnataka to Kerala. That it doesn't know, no. That is just all of a sudden, why it happened this last 1 week, 2 weeks before, all of a sudden from Karnataka to Kerala, so much rain, all full Kerala, full rain. It was a vortex form in the Arabian Sea. This is what people observed, monsoon people. But that is not a regular phenomenon, no. What is the, now I'm asking a simple question, which you should know after 2 semester courses. Whatever the PhD you are doing, but at least the meteorology course you did, no? So precipitation depends on what? Pressure, temperature, humidity, and not only that, the landscape. The monsoon is coming. Why it comes before first from Kerala, and why there is a lot of rain in the Western Ghats in Maharashtra and up to the Goa and all this? Why? Because of the landscape. The Western Ghat, higher altitude, Himalaya higher altitude. Lot of snow happens there, but not here. So higher altitude temperature is there, but even in the surface level higher altitude. So that is the topography. So at least few very important variable: temperature, humidity, surface level pressure, and temperature also 2 meter, 10 meter, whatever available to us. Okay, that all depends to form the precipitation. That is what, if you go inside this GCM algorithms, how we are calculating the precipitation inside after calculating the flow variables. There is some process, cloud resolving things and precipitation calculation, all those lot of things happens. So we are here, up to here it is stacked is okay, but for our data we can go one step ahead. Okay, this is the actually algorithm for stats here. I think I can skip this. I just told explaining. This is just a detail how we are doing. I can even tell you level 1, level 2, but algorithm I'm skipping. If you want, I can give, but I'm going to the concept here. Okay, overall algorithm of StatCRN, that we came from here to here, then here to here. Okay, so this is the 2 steps. So we are doing stacking, and this is the same thing training, same thing for testing. I'm doing. We all good here. Let me check anything else we have here. Okay, and how we do the validation, the extra variable I'm coming. So, but whatever we have done based on our image processing thing we have applied on precipitation, how we are going to say that this is better? Some metric. You know the metric, pattern correlation, MSE. This is what all told in the class. So we have to always compare. So till now, what we have applied is stacked CRNN as stacked SRCNN and SRCNN. So what is the correlation we got with the green one is the SRCNN, stacked SRCNN. What we used to do traditionally is linear interpolation. So we always, this is our baseline. You know, whenever you will do any machine learning algorithm, AI algorithm, you should have a baseline model to compare your model. Whether you are going the right track or unnecessary, you are wasting the GPU, which can be done simple on the laptop or even the Excel sheet. Okay. So this is the baseline. We have checked that SRCNN is better. And as Dong et al. And all said that if you go stack, this should give this gives better results. We are also getting in our precipitation. You see the correlation is even higher, and the higher peak and the bigger value also. So this is what, and same thing if we see the trend, MSE is less. These two metrics we have compared. So then you come to our this idea of precipitation. So now we have determined that temperature, humidity, this and that. So at least for the training time, we should tell our model, no, this is the precipitation, but this depends on this also. But you should have the data. So like 40 years data, whatever I took, how much, 40 years data, you should have all the variable available for all 40 years for the training purpose. So first thing we took the elevation. Elevation is fixed. It's not changing. It's just one value, one single file. The height is not changing any hills like Palmati Hill or whatever hill. We know that what is the elevation. Okay. But generally we are taking the elevation up to the whatever the resolution data we have, 25 kilometers we have. So 25 kilometer elevation. So we will say, okay, Mumbai is this elevation, Pune is this elevation, and Rajasthan, Jaipur is this. Each city or something within 25 kilometers each grid, we have this information. We can give. This is for our benefit as a meteorological data. So you see this. This is what the figure I made. That figure was from, I think, from Dong et al. This is from the some paper literature. This is our own figure. So what I have discussed, we take something, we using the SRCNN. Instead of SRCNN, we can go to the stacked SRCNN. 2 SRCNN. So this whole thing I put it here. If you see the symbol, this is one SRCNN. This is one SRCNN, another SRCNN. Okay. Now what I am saying that we will keep stacked SRCNN because it is giving better results. But again, we will give topography as an input for the training time. So when we give the topography as an input, it is really giving the better result. If you see, this is the SRCNN and this is the deepest. So picture is better here. So the resolution is better. So more information we are getting and more closure information. How we will check this, whether the information is better or not, we will check with the ground truth. So we check directly from the original data and the gridded data, whatever is provided by the IMD, because it is still 25 kilometers. We have the data available. So what is the time? Yeah, already. So people will sleep after that, I know. If I speak too much. Okay, so I will just stop here till the deep SD. So the whole story what I told, one thing you remember, the data pre-processing is different for the each particular data. Whatever the data you have for your particular research. Okay. Then the data downscaling using the super resolution CNN. We did the stat CNN, then multi-input. In the multi-input, we get the better results. So now you see, this is the 100 kilometer, 1 degree. This is the linear interpolation we used to do before. And that is our ground truth from where we have to compare. It should, anything we are applying for the downscaling, we should get this kind of result. Linear interpolation, you can see, we are nowhere closer to that. But SRCNN, the patches are coming closer. But then stacked, even closer. The deep SD, you see this western Ghat area. The whole pattern came up to here. Okay, but still we could not catch this one. This is only one spot. Here there are so many spots here. But till last year we had only these algorithms, 2-3 algorithms. We compared all these things. 3 SRCNN, stacked SRCNN, deep SD. We found the deep SD is the better for the downscaling. Okay, so see the statistical things. Now we are comparing 4 instead of the 3. So black one is the deep SD. So till red we have checked in the last slide. Now you see the deep SD. We are going even 0.8. 0.8 correlation is better. How much we are getting now in the this 12 kilometer CFS? You know, the dynamical model resolution is the correlation is going up to 0.7. So really very good. 12 kilometer, or not only 12 kilometer, even 33 kilometer. They are also going very good correlation. So we are already beyond 0.7. So that means 80% accuracy, and see the error is less. So the whole story for today in 1 hour, that we learned that why we need the downscaling. No?
Yes.
Priyanka,
Yes.
what? Why we need?
Downscaling for focusing on the particular region.
I mean, particular region focusing, then it's a dynamical downscaling using the regional model.
Yes.
But downscaling meaning, our aim is to get the local projection, because our grid will be smaller. So we hope that we will get the extra information. Instead of 1 point, we will have the 4 points in that particular location, particular city. That's why we need the downscaling. Okay, so we are doing the downscaling statistical. We are now moving to the AI/ML machine learning downscaling. Okay, so in the machine learning, what is the advantage we have seen even in this graph? We are getting better information, no, compared to, if you see here, see the linear interpolation. So linear interpolation and the deep SD, this is better. So this is the I mean advantage of the machine learning. But remember, when we talk about the forecasting and all, I don't know whether you learned forecasting using AI/ML in the class, but we never think that we can totally shift from dynamical to AI. That is not even true. We don't know. But at least in downscaling, we are in the good situation. So I have told these 3 methods. Do you think that is the end of the story? I told 4 comparison, baseline, 3 more methods. You think that's a good work? Yeah, that's very good. Researchers had done. So many papers came. If you see many papers on the downscaling, people have done the temperature downscaling also, I think. So that is done. So we are in a good shape. We can apply. What we can apply here, where we can apply this? I told no, we are running the forecast in 33 kilometers. So I'm saying that whatever the forecast is coming from the CFS and the GCM model, CFS, GFS, whatever, and then we are giving this information to the through the media to the common people. So instead of that one, we can give a higher resolution information. No? But is it ready that we can give this information and tell to IMD people or tell to government of India, okay, whatever the your output is coming, apply my algorithm. Instead of 33 kilometers, you give 10 kilometers. Is it proved now? We don't know. It is not end. Research is not end till we have done lot of. Once it goes to operational, it requires too much rigorous testing. Even any models, whatever the model is, sort of extended range, it was handed over to IMD 5 years before. But before that, so much research has been done. This whole, we have the group extended range, how many scientists were working. When it was really many years, it is giving the right forecast. Then it was handed over to as a operational to the IMD. So we are very good situation that DPST is working. We cannot say this is the end or we don't have any better method. In the next class, I will tell even better method. Better than this at least. Even I will say just a hint. DPST was published in January 21. February 21, another paper came. They said it is better than DPST. Somewhat better than DPST. Within 1 month. And within India also. We were not knowing each other. So this is not the end. We still have a lot of things to do. Lot of new algorithms are coming in the image processing side. So that can be applied. So in the next class, I will tell about more. And I'm planning, if we have time, I will also go to some code, how we are running. Mostly, I think on the Jupyter node or something, or direct